In this video, we'll be working with KSPs and solubility. So in this first example, we'll be calculating a KSP solubility ion product from the molar solubility when we're given the molar solubility. So if you're given X, or in some textbooks they call it S, and then asked to solve for solubility, you're given the amount of ions that the mostly insoluble compound is making. So you're getting the number that goes to the right side, the ionized side of the ice table. You're given the change is what you're given out of initial change equilibrium in the ice table. So remember, solubility tells you how much of the solid is dissolved. So how much of the solid is dissolved regardless of what you started with. So in other words, X is the change in the ice table. So let's do an example problem. So here's bismuth iodide. The solubility is 1.3 times 10 to the negative fifth. So let's start by setting up or writing out our reaction. And we'll write Bi, bismuth makes a 3 plus, and the iodide ion is a 1 minus. So when I balance it, I'm going to have 3 iodides for every 1 bismuth, and this is going to play a big role in how this is done. So we're going to go ahead and X out our solid in our ice table, since it's not going to have any effect on the equilibrium, the amount of solid. This is going to be 0. This is 0. The amount of iodide ions goes up by 3x, whereas the bismuth ion goes up by 1x. So at equilibrium, bismuth will be x, the iodide ion will be 3x plus 0. Okay, and now we set up our Ksp expression, and I always like to write out Ksp for this, and I'll tell you why. I see a lot of students make mistakes on this part, so bismuth 3 plus, and sometimes students they don't cube or square things. It's because of this 3 right here that goes right there. Now this number right here goes in right here, so it's actually gonna be 3x cubed. And I see this mistake a lot. Students they'll forget the 3 here, they'll forget to cube it, and they won't cube the 3 and the x, they'll just cube the x. But the 3x actually goes in right here for this term, for the concentration of I. So I just wanted to make clear on that, make that clear. So this is going to be x, okay, and then parentheses, we put this number right here, 3x, and then the whole thing gets cubed. So that cube actually gets distributed to the 3 and the x. So this actually is going to be x times 9x cubed. I cannot cube a 3. So it's 3 times 3 times 3, which is 27. So it's a good thing I checked my notes. So so that's going to be 27 x to the fourth. And we were given x. We were given this number. I like to clean this all up first, and then write x equals. And then I have, we're asked to calculate Ksp. Sorry. So Ksp then equals 27 times 1.3 times 10 to the negative fifth to the fourth power. So I'm going to get my calculator. And then I'm going to go 27. So 27 times 1.3 times 10 to the negative fifth, and take that to the fourth power. Okay, so I should get 7.7 times 10 to the negative 19th. 7.7 times 10 to the negative 19th. And KSPs, just like all the other equilibrium constants, are unitless. Okay, so I'm going to try the next problem. And here I'm going to be calculating the solubility from the KSP. So in this problem, I'm given KSP, and I want to know how many ions this is going to make based on this number. So, and it says ignore any acid-base properties. As you see, this is the phosphate ion that's going to be created, and this could interact with some H3O that's in the water. So if you have neutral water, H3O is actually equal to, this is actually talked about in our the next video. This is actually 1 times 10 to the negative 7th molar, and it could interact with this number because they're both so small. So, but in this problem it says ignore that fact, or ignore that variable. So I'm going to do this like normal. Okay, by writing out my equilibrium expression. So write the ions first. Okay, take your time, write the ions first, and then balance. So I'm going to have my 3 right there and a 1 right there. So ice. So this is, I'm going to X that out. This is 0. This is 0. Nothing is there yet. So this is going to go up by 3x, and the phosphate ion will go up by x. Okay, so this would be 3x, and this is x. So now, this time I'm given Ksp, and I need to solve for x here. So I'm also going to solve for the equilibrium concentration of both ions. Okay, once I know x, then I just times it by 3, and then I'll have my Ag concentration at equilibrium. So I'll write 1.8 times 10 to the negative 18th equals Ag plus cubed times the phosphate ion. Okay, so this is going to be 1.8 times 10 to the negative 18th equals x equals 3x cubed times x. So let's clean this all up, and I get equals 27x to the 4th. Okay, and so now x will equal 1.8 times 10 to the negative 8th over 27. So divide both sides by 27, and then take both sides to the 1/4 root. So this is going to be, or the 1/4 power, sorry. Okay, so this is going to be x4. Okay, and then we're going to go to the 1/4 power on both sides. Okay, so take out my calculator again. Okay, and this is how I like to enter it all in one shot. So, and so I'll use this fraction form in my calculator. So 1.8 times 10 to the negative 8th over 27. Put that in parentheses. Now I go to the 1/4 power, and I get, for my answer, I enter, this is actually to the 18th. I entered it wrong. So this is to the negative 18th, my Ksp. Okay, so insert 1 there. Okay, I knew my answer didn't look right. It was way too big. Okay, so this looks right. So 1.6 times 10 to the negative 5th. Okay, the mistake I wrote was I lost the 1 right here. So x is 1.6 times 10 to the negative 5th moles per liter. Textbooks, for some reason, they don't like to write molarity. They like to write moles per liter of ion dissolved. So this is the solubility. Okay, and it also asks calculate the equilibrium concentration. So for Ag at equilibrium, my Ag is going to be 3 times that number. So it'll be 3 times 1.6 times 10 to the negative 5th, or 4.8 times 10 to the negative 5th moles per liter. And my phosphate ion will be x, or 1/3 of what Ag was, which is 1.6 times 10 to the negative 5th moles per liter. So those are my 2 ion concentrations. Okay, so just to recap very briefly, is watch out for these because this is different than our acid-base chemistry where we were always working with 1-to-1 ratios. So these are going to be some number a lot of times because of these screwy charges that they make. And the other thing is, and you saw me in the previous problem, I messed up on it too, is because I couldn't cube the 3 right. So is make sure you insert this for this term. And I found it's very helpful just to write this part out. You make way less mistakes like that. It's super, super common as I see this not plugged in right correctly. Okay, and then the calculator, these calculators can enter so much data, so many numbers into one function that just take use of that fraction form and enter it in one big blob like that. It makes it easier to me. All right, so here's the your turn question. So one is, this one is like the one I just did. We're getting Ksp given the molar solubility. I forgot to raise that exponent, so that's to the negative 15th. And then this one, we're given Ksp, and we're asked to calculate the solubility. Okay, see what you guys come up with on that.